Hello everyone. This video corresponds with section 2.2 from the textbook Math in Our World, the 3rd edition. In this video we will continue our discussion of some basic set theory concepts. In this video we will talk about subsets, and in the next we will talk about set operations. Alright, first of all, let's talk about the idea of a universal set. This is basically the set which provides some sort of a context for your problem. So when we talk about, for example, the set of, let's say maybe freshmen. Okay, the set of freshman students. Well, it would be helpful to have some sort of a context to give some more details about what exactly we mean. Because right now this set is fairly ambiguous. Do we mean the set of freshmen in high school, the set of freshmen in college, the set of current freshmen, the set of any student who has ever been a freshman? And it's not really clear what we mean. So what the universal set does is it provides a context or a larger set, and then everyone would know that within that problem you're talking about only sets which are a part of that larger set. So if I specified and said that maybe my universal set was the set of current college students, then it would be more clear what I mean by the set of freshmen. Alright, we'll look at a numerical example, but first of all the definition. The universal set, symbolized by the capital letter U, is the set of all potential elements under consideration for a specific situation. So you'll see from problem to problem that this universal set will change. Just as in different conversations you have different contexts or different groups of people that you're talking about. Alright, here's an example. If the universal set is the set containing 1, 2, 3, 4, 5, 6, 7, and 8, find the set of all even numbers in the universal set. So we're ignoring all of the other numbers and we're looking only at things in this universal set. This is the larger context for our problem. And then from there we want to find the set of all even numbers in that universal set. So this set would be, we would just list all of the even numbers in that universal set. And notice I'm completely ignoring things like 10 and 12 and 14 because those are not in the universal set. Alright, Venn diagrams, you're likely to have used these before. These are named after the mathematician John Venn, and he used these as a way to organize and to visually describe sets. You've probably also seen these in different contexts as well. Okay, so on the left we have a figure which represents a universal set, and we use this rectangle to talk about the universal set or the kind of the context of our problem. So you would look inside there and any elements or numbers, letters, etc., things that you see inside, those would be all of the things that are in the universal set. So this one is depicting our universal set from the last example. Alright, now we can also have sets within the universal set, so pieces or portions of it, and here is set A, and notice that this is the set of even numbers in the universal set. So that is also the one from the last example. Alright, and then notice we also have some elements 1, 3, 5, and 7, which were not in the set of even numbers, but they're still in the universal set. Alright, this leads to a related concept, the idea of a complement. And the complement of a set is the set of all the elements in the universal set that are not in that set. So it's kind of like set and then not set. Here's the symbol for it. Whatever your set is, you put a little slash. It's kind of like an apostrophe, but just straight, not curved. Right? And that you would read that A prime. Or also a complement, and that's anything that's not in set A. Okay, but we're always talking within the context of the universal set. Alright, here's another way to say this. In set builder notation, the complement of a set is any element x such that x is in the universe but not in the set that we have named. Okay, so if I looked at figure 2.1, this one, and I was trying to describe a complement using the listing method, right, I would look for elements which are still in U, still in the rectangle, but which are not in A. So those would be the elements 1, 3, 5, and 7. Okay, and then notice on the right, a complement is all of the space outside of set A, but still inside the rectangle of the universal set. All right, let's practice. We'll find the complement of set A and then draw a Venn diagram to illustrate the universal set and a complement and set A. Okay, so to find a complement, we look at the universal set and we basically disregard anything that's in set A and see what's not in A. All right, so I'm just going to cross off things that are in A, W, Y, and Z. And then whatever's left is a complement. So a complement is the set containing V and W. Oh, I'm sorry, V and X. Okay, now let's make a Venn diagram. So we need a rectangle for the universal set. And then in one of the bottom corners, it doesn't matter which one, you write a capital U for the universal set. And sometimes it's italicized, so if you can make it a little slanted, that's great. Okay, we have one set that's been named. We have set A, so we'll draw that. And then usually kind of on the border or right next to it, you write the name of the set. And then because it's not entirely in or out, that helps to make it clear that that's the name of the set and not something in the set. Okay, and then inside the circle, we write things that are elements of set A. So we have W, Y, and Z. And then outside the circle goes A complement's elements, V and X. And you can write those anywhere you want, but notice we have to write everything still in the rectangle. So now if you looked at just the rectangle and you ignored the circle division and things inside, you should see all 5 elements in the universal set, and we do. Okay, and that's it. All right, let's talk about subsets. Sometimes we have sets that are naturally contained in larger sets, so we needed a word for those, and those are called subsets. So some examples are the set of students taking a college math course. That's a subset of the set of all college students. Okay, so students taking a college math course are automatically considered to be college students. The set of cats is contained in the set of animals, so the set of cats is a subset of the set of animals. Okay, a definition for subsets. If every element of a set A is also an element of set B, then A is called a subset of B. Right, the symbol this, it looks like kind of a less than or equal to symbol, except it's curved. All right, or like a sideways U. Right, and that means a subset. All right, so if every element in A is also in B, then we write A is a subset of B. All right, so we could say the set of cats is a subset of the set of animals. All right, and it may help to almost think of this as how you would use the less than or equal to symbol in math. So you may recall that the pointed end or the smaller end points to the smaller number. So for example, 5 is less than or equal to 8. Right? And it's the same with subsets. The smaller one goes next to the curved side. Okay, so cats is contained in this larger set on the right, the set of animals. All right, here's an alternate definition. This one may also help for some of the trickier examples. We can also say that A is a subset of B if there are no elements in A that are not also in B. All right, so you may want to write these down and refer back to these. These are some of the trickier concepts from set theory as you're getting used to these. So refer back to these and maybe read them a few times or go back to them after we've tried a few examples and see if that helps. Okay, a couple examples. the set containing 3 and 5 is a subset of the set containing 2, 3, 4, 5, and 6. All right, so let's compare with our two definitions. To be a subset, every element of A has to be an element of set B. All right, so is every element here, this is like taking the kind of the place of set A, and here's set B. Is every element in set A also an element in set B? Okay, and yes it is. 3 and 5 are also in set B. Okay. Our second definition, there are no elements in A that are not also in B. Okay, so I don't see any elements in A that are not in B. Okay, now if I had seen like a 7 in set A, then I know it's not a subset because 7 is not also in B. So you're just checking to see, did all the things in A come from B, or is there nothing in here that's not in here? Okay, the second example is the set containing 3 and 5, a subset of the set containing 3 and 5. And yes, this is a true statement. So again, according to our definition, all the elements in here are from this set on the right. And there's nothing in the set on the left that's not in the set on the right. Okay, this would be similar to the example if we had 5 is less than or equal to 5. When those are actually equal, that's a true statement. So you see that little line under the less than symbol, that's the part that kind of indicates that it's less than or equal to. And so in our example, that little line under the subset symbol tells us that it's okay to actually have two sets that are equal to each other. That's considered a subset of the set on the right. Okay, the third example is the empty set, a subset of 1, 2, and 3. Okay, this is a true statement, and this is the one that it's helpful to look at the alternate definition. All right, so I'll write that example here. All right, so it's hard to use the first one to say every element in this set is in here, because this set on the left doesn't have any elements, so that's weird to think about. But if you look at the second one, there are no elements in A that are not also in B. Okay, that makes maybe a little bit more sense. There's nothing in this first one that's not in set B. Okay, and like, I guess it's weird just because there's nothing in there. Right? You may also just want to memorize this fact that the empty set is a subset of other sets. All right. So basically, what I'm just looking for is I don't want to see any odd things in here that I didn't get from this set. Okay, and if I don't have anything in here that's not from here, then I'm good to go. Okay, an example of one that's not a subset would be like 1, 3, and 3, 4, 7. Okay, so I have this kind of this oddball one that didn't come from the set on the right, so that's not a subset. Okay, so let's look at all of the possible subsets of the set containing X, Y, and Z. All right, so this chart is from your textbook, and this organizes the subsets based on how many elements are in them. So first of all, we can make a subset. We're just going to be choosing elements from our main set. All right, so we could choose all 3 elements. It is a true fact that the set containing X, Y, and Z is a subset of itself. Okay, we pulled all 3 of these elements from the set on the right. All right, we could also take 2 elements out of that set, and all of those would be subsets. All right, so examples would be the set containing X and Y, X and Z, or Y and Z. All 3 of those are subsets of the set containing X, Y, and Z. We have 3 subsets with 1 element. Okay, so the set containing X is a subset of the set X, Y, Z. And then we always have this weird case. The empty set is a subset of all of our other sets. Okay, so no matter what set is on the right, this is a true fact. Okay, so there's nothing in the empty set that's not coming from this set. Alright, so if you count those up, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 subsets for this set. Okay, you could think of it as like 8 smaller collections of things taken from that set. Okay, let's try it with a different one. The set A equal to the set containing American Idol and Survivor. So the set has 2 elements. And just to review, we can say that its cardinality, the cardinality of set A, is 2. It has 2 elements. Okay, so let's list all of the possible subsets. Alright, so I start with braces and then I just fill them with things from that set. Well, one option is to fill it with nothing from that set. Okay, that's the empty set. I could fill it with one thing. Alright, I could fill it with American Idol. Or I could take out just the set containing Survivor. Right? Or I could take the set of everything in that set, American Idol and Survivor. Alright, so I can have one subset with 2 elements. Alright, and then that's it. So I have 4 different subsets of that set. Alright, we have a symbol to indicate that a set is not a subset of another set. So for example, the set containing 1 and 3 is not a subset of the set containing 0, 3, 5, and 7, because we have this one single element 1, which is not an element of the set on the right. Alright, so it's that definition that there should be nothing in here that's not also in this set, but that's not the case. Alright, we have a 1 that's not from the set on the right. Okay, so that is not a subset. Okay, another concept is the idea of a proper subset. Alright, so while we have said that, let's go back to this one, we've said that a set is technically a subset of itself, but what we want to do is also talk about, well, how many of those subsets are actually strictly smaller than the set itself. And that's the idea of a proper subset. It is a subset, but it's actually not the set itself. Okay, if we looked at the American Idol and Survivor example, we had 4 subsets, and only 1 was equal to the original set. Okay, the other 3 were proper subsets. Okay, so these 3 are proper. This one is not proper because it actually equals the set itself. Okay, so to be a proper subset, a set has to be, we'll use A and B. A set A is a subset of B, and it's not equal to B. Here it is in symbols. It's a subset of B and not equal to B. And then we say that it's a proper subset, and we have a different symbol. Okay, it doesn't have the equal to part of that subset symbol. Okay, and that's the part that tells us that it's not actually equal to. Okay, so it's like strictly smaller than. This is similar to the less than symbol. All right, it's not true that 5 is less than 5 because they're equal. Not true. But it is true that 5 is strictly smaller than 6. Okay, and it's also true that 5 is less than or equal to 6. So sometimes you can use both symbols. Okay, so here we have it in sets. Both of these statements are true. The set containing 3 is a proper subset of the set containing 3 and 4. It is a subset. It's made up of some elements. We've taken the 3 out of the set on the right. And it's strictly smaller than it. It's not equal to the set itself, so it is proper. Okay. Or we could also just say that it's a subset. It does fit that definition as well. Everything in the set on the left was taken from the set on the right. So sometimes you can use both symbols. Okay, so let's find the proper subsets of the set containing X, Y, and Z. Alright, so basically we just want to look at the subsets, but not count the one that actually equals the set. Right? So not that one, but all of the other ones. Okay, so we can have all the ones that have 2 elements, xz and yz, all the subsets that have 1 element, and then the subsets with 0 elements, the empty set. Okay, so there are 7 proper subsets. Okay, let's practice these symbols. You might want to pause this and maybe look back through your notes or the textbook and try some of these, and then we will talk about the answers. Okay, true or false? The set containing 1, 3, 5 is a subset of the set containing 1, 3, 5, and 7. All right, so all we have to check for, do all of these elements come from here? Yes, they do. So this is a true statement. That is a subset. Okay, is the set containing AB a proper subset of the set containing AB? So we have to check 2 things. Is everything from here, from the set on the right? And then we have to make sure that the sets are not actually equal to each other. Well, they are, so this is a false statement. If we wanted to correct it, we would have to use this statement, the one that has a little line under it that shows that they can be equal to each other. Okay, part C, the set of all x such that x is an even natural number greater than 10 is a proper subset of the natural numbers. All right, well, the set on the left, even natural numbers greater than 10. Okay, that's 12, 14, 16, ... Is that a proper subset of the natural numbers? Yes, it is, because this set does not actually equal the natural numbers. It's missing all the ones less than 10, and it's missing all the odds. And, okay, so they're not equal, but all the ones on the left were taken from the natural numbers. It's a part of that larger set. It's contained in it. So that is a true statement. All right, the set containing RST is not a proper subset of the set containing T, S, and R. That is true. And that is true because those sets are equal. Even though the elements are in a different order, it's the same set, so it can't be a proper subset. All right, set E, the set containing Lake Erie and Lake Huron, is not a proper subset of the set of Great Lakes. Well, that is a false statement. Okay, Lake Erie and Lake Huron are 2 of the Great Lakes, so this set was taken from the set on the right. And these sets are not actually equal to each other. So that is a true statement that, it should be a proper subset. Okay, so it's false that it's not. All right, and F, is the empty set a proper subset of the set containing 5, 10, and 15? All right, this one is also true. Okay, the empty set does not equal the set on the right, but we can use that second definition of a subset, right? There are no elements in the empty set that are not also in this set. All right, or if you want to think of it as kind of like there's, nothing, or let's say it this way. Something is a proper subset if, like, you can take a box that represents your set and you just want to fill it with things from the larger box on the right. All right, and if that's the case, then that is a subset. All right, in part G, the set containing U, V, W, and X is a subset of the set containing X, W, and U. Well, that is false. All right, and the reason is that we have a V here that didn't come from the set on the right. Okay, and then finally, the set containing 0 is a subset of the empty set. All right, well, we have this 0 that's not in the empty set. All right, it didn't come from the empty set because there's nothing in the empty set. So therefore, it's not a subset of the empty set, so that is false. All right, a note on some of these symbols. It's important not to confuse the concept of subsets with the concept of elements. So the statement 6 is an element of 2, 4, 6 is a true statement since 6 is an element of this set. Okay? But it's not true to add in those set symbols and then say that the set is an element of the set on the right. Okay, so you only use, okay, this is false. You only use this element symbol if the thing on the left is an element and the thing on the right is a set. Okay, if you want to compare two sets, then you have these symbols. You can say that it's a subset, a proper subset, not a subset, or not a proper subset. So those are your four choices if you're comparing two sets, one on the left and one on the right. Alright, and I think we'll end with the number of subsets and proper subsets that a set has. Alright, so we'll use inductive reasoning to find the relationship between the number of elements in the set and the number of its subsets. Alright, so we've already looked at a couple examples. This set with 3 elements, x, y, and z, we said that there were 8 subsets, and there were 7 proper ones. We just throw out the set itself. The set itself is not proper. For the set with 2 elements, okay, recall back, this one had 4 subsets, okay, and only 3 of them were proper. The set itself is not a proper subset. Alright, how about a set containing 1 element? What are all of the subsets? Okay, well, the set itself is a subset. Okay, that's a set containing 1 element. That's the only 1 element subset. And then we also have the empty set is a subset. So this one has 2 subsets, and only one of them is proper. This set, the set itself is not proper. Okay, how about the empty set? Okay, well, the empty set itself is a subset of itself. Okay, this is a true statement. Okay, so there's no elements in the empty set that are not also in the empty set. Okay, so it has 1 subset, but it's not a proper subset because it's equal to itself. Alright, so it actually has 0 proper subsets. We can't make any smaller subsets than that one. It's already as small as it gets. Okay, you may want to try a set with 4 elements. Maybe try x, y, z, w. Okay, list out all of the different subsets. How many can you find? Okay, how many proper ones are there? And then take a guess as to what is the relationship or the pattern here. What does the number of subsets have to do with the number of elements in the set? So you're looking at these numbers and the number of subsets. Okay, maybe pause and try this, and then we'll go over the answer. Okay, so we can actually show, at least using inductive reasoning, we haven't proved it, we can show that there is a little formula here. Okay, a set with 0 elements, the empty set had 1 proper subset, a set with 1 element had 2 subsets, okay, a set with 2 elements had 4 subsets, a set with 3 elements had 8 subsets, and if you tried this, a set with 4 elements, you can make 16 different subsets. Okay, so you can see this pattern, we're kind of going up, multiplying by 2's. Alright, this is 2 to the first, this is 2 squared, 8 is 2 cubed, 16 is 2 to the fourth, and then you may also remember that 2 to the 0th is equal to 1. Right. And then notice that these numbers, the exponents, match the number of elements in the set, right? So for a finite set with n elements, the set has 2 to the n subsets, and then you just subtract 1 to find the number of proper subsets. It's always 1 less than the number of subsets. All right, so for example, let me make sure I'm not skipping ahead here. 4, 6, yeah. Okay, so if we had the set 1, 2, 3, 4, 5, all right, I no longer need to list out all of the subsets to figure this out. I would simply count and see that the cardinality of this set is 5. So it has 5 elements, so there are 2 to the 5th, or 32 subsets, and then 2 to the 5th minus 1, or 32 minus 1, or 31 proper subsets. Okay, find the number of subsets and proper subsets of the set containing 1, 3, 5, 7, 9, 11. Okay, so step 1, you count the number of elements in this set. Right, so its cardinality, 1, 2, 3, 4, 5, 6, is 6. So there are 2 to the 6th, or 64 subsets. And then there's always 1 less proper subset, so there are 63 proper subsets. All right, and we actually don't even need to know what those elements are, we just care how many. So if you knew that the cardinality of set C was 8, that's enough to find the number of subsets and proper subsets of set C. Okay? So subsets, there would be 2 to the 8, since there are 8 elements, and I think that's 256. Okay, 256 subsets. And then proper subsets, always 1 less, 255. Okay, and that's it. Alright, we'll stop there. So this is quite a bit of material in that video, so I would encourage you to look back at your notes, review the definitions of subset, proper subset, all of the different symbols, maybe try the additional examples in the textbook, as well as the practice problems, and then you can let me know if you have any questions.